hardware we've used so far, what we're using now, and then Matthew's going to go through some code as well as, we'll try to go through the early stuff kind of quick so we can get to questions, because I think people probably have a good bit of questions. But so for us, actually, let me show you. We started really around 2018, 2019, working on targeting and vision. And we did so with this, the NVIDIA Jetson. All right, you might notice this is kind of big. So this, we custom code in Python. It was actually pretty good. That video that's kind of running is actually us using it prior to 2019. The problem we had is we actually burned 3 of these. We had lots of issues with power. We couldn't get really a good power situation going that didn't torch this thing in like a couple minutes. So any wiggling or anything would cause problems. So we actually went to Hatboro with this working pretty well for placing our panels, and 2 matches in, it didn't work anymore. So we had to go totally manual. But at that comp, a couple teams had Limelights, and Limelights were just coming out. We bought a Limelight. By the next comp, we basically switched over. All of our code that we had written was very adaptable because we had taken the same approach. So we were able to switch to a Limelight, and we ended up running that at our next competition. This is the Limelight in action. So this was us being able to place basically autonomously going in for pickups and places using the Limelight. Pretty quick. These things are hard to break power-wise, which is one thing I definitely recommend about them. The only issues we ever had with the Limelight were actually with the Ethernet pins. We had problems. Luckily at Worlds, one of the people on the team that built it gave us one to replace the one where we had an Ethernet problem. But outside of that, I think we still have our first Limelight 2, standard 2, and we still use them on development, and we kind of work in hardware where it makes sense as we're developing things. So we had a really decent amount of success. Prior to 2019, our team had never won a competition. We had never, walked out of an off season, a regular season, or anything prior to that. I think targeting was one of the things. It allowed us to really be able to adapt to a game, run quickly, be competitive. From that point on, we started to get much more, I would say, consistent in how we played each game by using some repeatable things that we had done in the past and just building on that consistency. In 2020, 2021, we actually did use machine learning using the WPI, what they call it, WPI Pi or whatever, but it ran on a Raspberry Pi. So using a Raspberry Pi, we could recognize where balls were for picking up. And then we were also using retroreflective with the Limelight for targeting. And again, we're able to keep continually building on our consistency. And then 2022 to present, especially in 2022, we made a switch from Python for our robot code to Java. We love Python. It was a great run with Python, but we could never get odometry to work really well. We could never get really the speed we wanted out of our code with Python. We came back from Worlds, and before IRI, we rewrote all of our code in about 3 weeks to go to IRI with Java, and we are not turning back. I think all the students will agree Java was a good change. It's allowed us to do a lot of things, and Matthew's going to show you much simpler, and we're able to take advantage of libraries and things in just a much more efficient way. So now we're using April tags to determine robot pose, and we're able to do some much more advanced things with our autonomous, so even beyond actual targeting within the game. So just sort of briefly, as a programming and strategy mentor, my focus with the team is simple first, understand it. Don't try to force ourselves into these situations where we're trying to do things that are overly complicated. Most of our success comes with in targeting with just simple aiming and adjusting, not with really elaborate, over the top movements or functions or autonomous. So to me, you want to really start with what are your key objectives that you're trying to execute, and what can you do kind of simply that allows you to build on that. And that's really, I think, what's helped us, again, be consistent and build on our success rather than like having constant resets. That we do experiment a lot. We split off teams to try things. We try things on different hardware. So we're not like Limelight all day long. We're running Raspberry Pis. We're testing with Orange Pi as well. We're getting, writing our own code, using existing software. So we're really trying to do everything, but then we apply it where it makes sense. This year is a good example. The last 3 games prior to this year, we had a lot of autonomous in game where we would recognize something, go in and pick it up, and that was all automated. This year, because of the way the game worked and the way our drive team ran the game, we left some things more manual. So our places are manual, but our lineups can be assisted. And so those things, we made that judgment based on practice. So programmers are always going to say, oh, we should automate everything. Let's make it all do this. Let's make it all do that. But I think it's important that you apply it to how it will work for that game and then your drive team in particular, getting them as much practice as you can. And then it's funny, these two are always up right next to where practice is happening, making code changes. And we're constantly evolving during practice, making it, just listening to your user. As I always like to say, you got to listen to the person that's operating it to understand how we can make improvements that will actually make an impact. So now we'll toss it over to Asa to talk about vision and hardware.
Yeah, I'm just going to go over some of the more common hardware and software options that we have for vision and that we've been using this season. So things like Limelight, Photon Vision with Raspberry Pi, a couple targeting things, and tuning your vision pipelines. So just to quickly go over Limelight, it's really popular among FRC teams because, it's very comprehensive. You have your camera, your LEDs, your computing all in one box, and you can basically just plug it in and have it set up in under an hour. So a core part of vision is targeting, as we know, and something that's about to be phased out but has been really important in the last few years is the retroreflective targeting. So the LEDs shine at the retroreflective tape and give you coordinates based on what you see in your camera feed. This year we now have April tags, which can serve the same purpose as the retroreflective tape, which can give you like pose estimates and coordinates for you to align in place. But a new feature they also have is pose localization. So each April tag is unique and they have their own pose coordinates. And by combining the pose coordinates as well as the angle that you see them with, you can estimate your exact position on the field. And you can do that because it has a 3D box that you can see in your camera. So when you do your vision, you have to set up a pipeline in order to set up your camera feed so that your camera feed will have to look a specific way with retroreflective tape so that it's illuminated and everything else is black. And I'm only talking about retroreflective pipeline because April tags work much in the same way, just that there's another separate tab for 3D visualization. So when you first set up your camera feed, you have your input, which you will need to change. You can set up your exposure, your black point, your LEDs, and the type of pipeline that you want to use in order to do your targeting. After you set that up, you can specifically determine which hue that you want to target toward, which will always be that reflective green color. And you can do that through the Limelight software by selecting it with an eyedropper tool and then including pixels it didn't pick up as well as removing pixels that you did not want. You can also change the hue range and the saturation and things like that to more finely tune your targets. After that, you have your vision contours, which is basically a box that shows up around your targets. And sometimes, during a match, thresholding doesn't quite filter out the windows or the sun or other bright objects that may look like the retroreflective tape, but will mess up your targeting. But you can filter those out through contour filtering, which essentially if you know that your contour, like the shape of your target, should be a certain width, or like if it should be longer, then you can exclude tall contours that might come from windows or other sources. And after contour filtering, you can adjust your output to specific features of your robot. Like if your shooter happens to shoot left of your target, you can calibrate it so that the pose coordinates you're given are adjusted based on that. Limelight can also do other targeting, such as game piece targeting with machine learning, which is technically natively available on Limelight, but it's very slow. So what you can do is add a Google Coral USB attachment, which is a specific like TensorFlow coprocessor, and it will accelerate your machine learning inferencing because it can do much faster operations, like 4 trillion operations a second for a half watt. And that way you can identify the game pieces on the field with machine learning. And I'm also going to go over Photon Vision, which is an alternative vision software, which is a lot like Limelight. It serves much of the same purpose, but it works with various cameras and coprocessors, which can be really helpful when Limelight is like $400 a camera, and that might not be reasonable for a lot of teams. And specifically emphasizing Raspberry Pi because it's a lot more affordable, even if it's never in stock. It's also continually improving its hardware as well, and it also has a diverse set of software options. Like you could go with a stable software that's pre-existing, or you could write your own. Photon Vision software, a couple differences it has with Limelight is that you can have multiple cameras per coprocessor. So instead of every time you want like maybe a front camera and a back camera, instead of having to buy 2 coprocessors for it, you can just run both cameras on one. And it can also identify and select up to 5 targets at once, which is helpful when you want to have an aiming redundancy and make sure your pose and your position is at the correct spot. So this is what it looks like, and you can see it's very similar to Limelight. It has the input, the thresholding, the contours, and the output, as well as the camera feeds and things like that. And with all of this software stuff, you also have your code, which will be talked about by Matthew.
Hi, I'm Matthew again. Anyway, so I'm gonna walk through some code examples for how to make use of all the stuff that we've kind of gone over through this presentation. Okay, so accessing camera data, right? We have these great cameras. They're sending all this data, but how do you get it, right? So Limelight, at least, uses network tables to send the data over. It's exactly what it sounds like. It's a collection of tables that get sent over the network to your robot, pretty much. Yeah, so each camera, like the Limelight, will have its own table in network tables, and it'll have information in topics in network tables. Anyway, so these topics, you can read from them, like the Limelight can send over X and Y position, and you can also write to them, so you can set the Limelight's pipeline, which is crucial if you want to do more than one thing with the Limelight, or if you just want to have like one state where the Limelight's off, so it's not like shining. That might be nice. Anyway, so this is the first thing you'd want to do if you're doing this. You want to define your subscribers and your publishers in your class, in your subscript system, your command, wherever you want to do this. So we have for this example, I'm just going to be doing the X position of the target, the Y position of the target, whatever pipeline we're on right now, whether it has targets or not, which you'd think would be a Boolean. It's an integer because of, I guess, how network tables works, or however Limelight decided to set up the API. And then we have our pipeline publisher for changing pipelines. So basically, for getting these, what you're going to want to do is you're going to want to find the default network tables instance using that up top. And then you kind of use a path-like pattern to get your subscribers. So basically, this here, network tables.get integer topic. This is our table, this is our topic in the table, and this gets a integer topic, and then you subscribe. The 0 in there, basically subscribe gets you a subscriber with 0 as the default answer if there is no topic or there just is no result yet. And then that has targets is an object which you can call a get method on. And the same thing applies for this. This is your X position, Y position. This is how you would get your pipeline. This will let you know what pipeline you're on in case you want to check or confirm that you're on the right pipeline before you say start targeting, right? And then this is a publisher, takes no default because you're the one sending the data and you publish that. I'll show you on the next slide how you actually do this publishing stuff. So basically, you can just get the pose like that. So if you had a target, your line is looking at a target. That's your X pose, that's your Y pose. That would be your pipeline. And when you want to set your pipeline, you can set it to 1 in this example, or 2 or 0. Pretty much anytime you want to change the pipeline from your code. Yeah, just call the get method or the set method. Very simple. Once you have those paths, those subscribers and publishers sorted out. This is the simplest way to aim. This is what we used to use a while ago. We've switched from it, but I'll just go over it for completeness. Basically, it's a pretty simple loop. If your robot's to the right of the target, it's just going to turn left. If it's to the left, it's going to turn right. You can see how that's going to get you to the target. Pretty much just an if statement, and you pretty much just get your target yaw, target X. And if we don't have any targets, we're not going to turn at all, because Limelight will kind of just cache the last target it saw if it sees no targets, and that'll just end up with your robot just spinning around in circles, which is probably not what you want to happen. It would be better if it just kind of stayed still, so your driver realized, oh, it doesn't see the target, I probably need to move. Some downsides, it's kind of slow in comparison to other methods, but it is very simple to implement. But this next one's also pretty simple to implement, so I personally would recommend the next one highly over this one. Oh, okay. So the next one's a PID controller. What is a PID controller? Well, it's a controller that has 3 things: a proportional component, a derivative component, and an integral component. I'm only going to really be talking about the proportional component, but basically the controller takes in your error, right? So if you're to the right of your if you're off from your target, how much you're off from your target, pretty much. And then it outputs a correction value that your robot can then take to correct and get towards its target. This works for things other than just vision, like controlling motor speeds. That's the only example I can think of right now, but it's very versatile. Correction is proportional to error if you're just using P. And basically, whatever you set the proportional value to, that's going to be the proportion. So if you're 1 meter off from your target, and you knew that, and you set it through a PID controller with a P of 1, it would give you a correction value of 0.1. It's much faster than a loop because it can actually take into consideration how far away from your target you are. So it doesn't just go the same speed the whole time, and it'll home down on your target a lot faster. Also significantly less jittery. It's also still pretty simple to implement due to classes that exist in WPILib that make it pretty simple. So what we do, we use Java. I mean, it's already been said, but so in this, with our Java PID controller from WPILib, we basically just create it with a P of 0.1, an I of 0, and a D of 0, in that order, PID. And then we initialize it with our goal of 0 and our tolerance of 2 radians. Basically 2 degrees. 2 degrees, not 2 radians. 2 radians would be a bit of a big tolerance. And then all we do is we get our X position. It's inverted because on our robots, at least, we'd have positive turning, meaning turning to the left, but Limelight has positive as to the right. So that's why it's inverted there. And then all we do is we take our current target, calculate it using the PID controller, and that's our turning speed. And now, if it's already at its set point or goal, we set it to 0 so it doesn't turn, right? If it's at the goal, we don't want it turning. And otherwise, we just set it to the turning speed. So then it'll go to its goal. A profiled PID controller would be the step up from this. It's used to limit acceleration and velocity. So you pretty much give it an acceleration that it can take and a maximum velocity that it should take, and it'll figure out a path that your robot can take towards the target that follows those. It's best when your output is in speed or rotational speed, and your input is in position or angle, and those are best when paired with each other. They don't need to work like that, but it's best if they do, so it can figure out how the acceleration works, and so the units are all correct. There's a lot less overshoot than if you use a PID controller. It has a tendency of landing pretty much on the dot, and it's also more complicated to implement, though. I still recommend going for it, though. So for this profiled PID controller, you're going to need a trapezoid profile constraint, which is this class right here. Basically, you have your max velocity, which here is 3 meters per second, and here are max acceleration, which is also 3. Anyway, and then you also have your turning PID controller. This time, it's a profiled PID controller. You still have your P, I, and D, but this time it takes in your turning constraints. So it's going to follow those. You set your goal, and you set your tolerance. So in periodic or execute, if it was in command, this being a subsystem, we get our X position, and then we calculate it again. But this time, instead of calculating our final velocity, we're calculating a correction. The tuning PID controller also calculates a set point, which is basically like, this is how fast you're supposed to be going right now. And the correction is based off of how far off we are from actually going that fast. So you add those together to get your turning speed. And then again, if you're at your goal, you don't turn. If you aren't, you do turn. Targeting April tags. So that was all kind of with code examples targeting retroreflective tape, right? Targeting April tags, it's really simple. You just change the pipeline like that. So that's all the changes you need to make to, instead of targeting a piece of retroreflective tape, target the April tag. They work identically.
Of course, that pipeline is set up as an April tag pipeline.
Yes, you set up the pipeline. There's no changes that really need to be made in the code. So pose localization, I know Asa already talked a bit about pose localization, but pose localization allows your robot to basically figure out exactly where it is on the field by looking at April tags, because the Limelight knows the location of the April tag, can figure out how you're looking off of it based off of the 3D data it's getting from the April tag. And that's useful for a lot of things. You can do relative scoring relative to the April tag, because you can get a field relative position from the April tag, so you can also get your position relative to the April tag. So you could say, I want to be to the right of the April tag, and you could score that way. Or you could just score using your field relative position and use the April tags to contribute to your odometry. This is how you would do that. We would set up our subscribers and our pipeline publisher. And this is a bit different, but basically, depending on which alliance we're on, the way we do it on our team is one of the corners is always 0. And if our alliance switches, the field basically gets mirrored in our code. But basically, this gets our position if we're on the red alliance. This gets our position if we're on the blue alliance. Limelight has 2 separate topics for those, so we don't have to do the conversion ourselves. And this one lets you know what tag you're looking at if you wanted to know. I have the default set to -1, so we can know when we're not looking at the tag. So this data comes through as a bot pose, and this is basically just a double array with length 7, pretty much X, Y, Z, your rotations, and I believe the latency is the last one. But basically, we get this if it's not there. Basically, the array isn't full, or we don't have our target. We're just going to return an empty optional to signify that we don't have a pose right now. We don't know our pose from these able tags, and it won't be factored into our geometry. If we do have it, we're going to get the bot pose 0, which is our x coordinate, bot pose 1, which is our y coordinate on the field. And then our rotation is going to be bot pose 5, which is our yaw. There's details about this on the Limelight docs too, because this is kind of very simple. You can get a 3D robot pose as well from this, not just a 2D robot pose. Overall, with Limelight, pretty simple to implement. It's basically set up for you. You don't need to do too much thinking about like where April tags are. Not much configuration either. So the future. So this is the future of vision targeting, right? What is it? Well, no more retroreflective tape. There's going to be lots of April tags because they're switching the class. We might do more cameras and machine learning. So I'm going to quickly cover those. Retroreflective tape, it's being gone in 2025. It lived a long life, 2011 through 2024. Yeah. April tags are going to play a much larger role, basically. The good thing is April tags, as I already said, can just be used as a pretty much drop-in substitute for retroreflective tape. You just go in, change the pipeline to April tag. You can target using any of the methods that you've been using for retroreflective tape. So that's very useful. April tags, yeah, they can substitute. That's pretty much all there is to say there. But buy retroreflective tape. It was fun while it lasted. We're also getting a new class of April tags. So that right there is the current class that they use. As you see, it looks pretty blocky. And then these ones have even more blocks. So that means more accuracy. And there's going to be more April tags because there's more ways to arrange the blocks. So there's a lot more April tags they'll use. This probably means they're going to be putting a lot of April tags on the field, a lot more than there were this year. This year there were like 8, I believe. Next year there will probably be more. The higher accuracy means that you're going to be able to do better pose localization with them, and it's a lot more likely you're going to be able to see an April tag at almost all times, which leads to, again, better pose localization. In the future, we as a team at least are thinking about using multiple cameras for April tags. This is a diagram of, I believe, Wildstang's Limelight camera setup. They have it so that when they're by the grid, they can actually see up to 3 April tags at a time, and at any time they're guaranteed to see 2 April tags, and they're always guaranteed to see at least 1. Maybe they're only guaranteed to see 1. Anyway, multiple cameras, you can always see an April tag, and this gives you extra precision from always being able to see that April tag. And if you can see 1 April tag from multiple angles or multiple April tags, that'll also give you extra precision. So extra precision is always good. Helps with scoring, helps with pose localization, and can help with accuracy in auto. I forgot to mention that, but that's very useful. Being able to know exactly where you are in auto so your robot doesn't like crash into the charge station. And then also machine learning will be done in the future. Probably. There might be game piece randomization in autos. I know they did that in FTC. Might be useful to know where the game piece is so that your robot can drive to it and pick it up and score well. That's pretty much it. So thank you.
A couple bonus things I'll throw out that we didn't mention when it comes to April tags. Resolution matters a lot. The camera itself matters, so you want to get preferably like a global shutter camera. Black and white's totally fine for April tags. So cost-wise, you can get something decent there with a decent resolution, but it helps a lot. You're going to want that higher resolution to see the tag further away. That's something we found, and you want to processor-wise. That's why we're going to be experimenting with Orange Pi as well as Limelight to try and get our frame per seconds up so we can process more quickly. But all that stuff matters. But the one thing we didn't say out loud that I know we've learned the hard way is camera position is very, very, very important. So Matthew kind of mentioned at the end, one of our issues this year was we had our camera behind our arm. And so about quarter of the time, our camera couldn't see anything because our arm kept passing in front of it. But we didn't build our robot with that in mind in order to make sure that the camera was mounted in a position that it would not be obstructed. So I think, you know how mechanical likes to tell us, like, you know, to wait. Tell them they need to make this decision early. Like, we need to know where our camera's going to be and how it's going to be played into our entire design, because it will be critical. If it's not or it's obstructed, it's not in a good position, cannot see a good field of view, you will not be able to use it very well. So that's where we have to work with the other teams and sub-teams of our teams and try to kind of all communicate to build the best robot. Getting that wider field of view, we think, is really important, especially as there will be more April tags. We noticed, you know, especially, so we recently switched to the Falcon Pro sort of program, and we've started updating. We've noticed less drift, but we dealt with drift a lot with robot pose and odometry. Like, so April tags, constantly checking and updating that is helpful. Like, it will reduce, you know, that drift. It'll keep you more in sync with where the robot thinks it is, and being true. So just a couple bonus things. I will also say we'll share this presentation on the Discord, the FMA Discord, for anybody that wants to check out specifically it. But we also share all of our code on GitHub, so we don't wait. It's all released the day we commit it and publish it, hopefully fairly frequently. So definitely check that out. Reach out to us on Discord, FMA Discord. You know, we're happy to answer any questions anybody has. If you have any questions. Yes.
If the robot is moving, we notice that the big flag recognition is kind of like gone.
No, so it can track it while it's moving, and it will update while it's moving too. Another bonus tip we found was any kind of obstruction to the tag the tag will go away. So if there's even just something in the corner of it, that's one thing that's like retroreflective. Like, you could have a kind of not great target and you could get enough of it to be able to target on it. With April tags, you either have it or you don't. And if you have anything like another robot's arm comes into part of that, you lose it. But if you're using it for like odometry, my battery's going to die. That's cool. Then, you know, you would just update when you get it back. It would come back.
Also, global shutter can help with being able to see April tags while you're moving. If you're moving while you have rolling shutter, that can distort the April tag, and the software might not be able to recognize it because of that. So that's another thing.
Yeah.
So that's why it's very important to choose the right camera for your April tags.
For sure. And also, there's actually two really great threads on Cheap Delphi. One that goes through all the cameras and another that goes through all the co-processors. And they actually have like what frame rates they're getting for the different like resolutions that they're using. So I could share that on Discord as well. But those have been really helpful for us. When we did machine learning, we were involved in a giant thread on WPI LibPy on how to use it for machine learning, and that is so helpful. So I definitely recommend like reaching out to other teams that you know are doing the things you want to try to do, or using Cheap Delphi or the FMA Discord, to reach out and get information, because it's priceless. Like, it's helped us so much, and kind of solving some of those bigger, trickier problems. Yep.
I know you had mentioned Orange Pi. I know a little bit about it, but more specifically, I know it's a software for the right now.
Oh no! So Orange Pi is actually another hardware device. Oh. It is a beefier Raspberry Pi. It has I forget the exact processor, but it's like an ARM processor. It's much faster. So I think. And again, there's a great chart on it that shows the comparison of the Raspberry Pi to the Orange Pi, but I'd say the Orange Pi almost outperforms it by like nearly double. So in the case where you want to do a dual camera like we're doing at higher resolution, you want to keep your frame rate high, you need something with either more processor or you need more of them. We're trying, and I don't know about everybody else, but with the entire world going swerve, we're running out of places to plug things in to get power. So we try to limit the number of coprocessors that we're running as best we can. Though, to be honest, we had 3 coprocessors on our robot this year, and we honestly only used 1, like most of the time. If we're being brutally honest with ourselves, but we had them mounted, so why not? But yeah, that's another big concern. So and cost. I think an Orange Pi is around $150, so significantly cheaper than a Limelight. Now, the one thing the Limelight's going to give you right now, out of the box, that the others really aren't, Photon Vision doesn't, at least yet, support, is the machine learning. But you do need a Coral, and Corals have been pretty hard to get a hold of. We just happen to have one from previous work that we were doing, so we were able to use that. So if you want to get into machine learning, I would either look at developing something yourself, because that's just fun. The training's the hard part, honestly, more than the code or the coprocessor. It's actually building a good model and figuring out. One of our students, actually, I'll have to put this out somewhere, but he's at E-Town, and he last year did a project of trying to build almost like Limelight for machine learning software, and they're making that available to teams too. So there's a lot of stuff out there. I think we're probably at time. But any last questions before we go? All right. Thank you guys so much. Have a great day. Good job. It's awesome.
It's only 10:40.
Yeah, okay.
People that switch. I mean, we're
The
here
one
to
of the
answer
one of
questions.
3 dudes just
What's that?
So when we follow,
The one of 3 dudes walked out.
so we follow, we can tell the driver team that we're at Taco Bell. In case they didn't know.